Hello. The purpose of these sets of videos is to give you the background on matrix algebra so that, one, to just have you set ready to go to class, and two, it's an accompaniment to the appendix in Warner that you are encouraged to read as a part of this class. So you do need to watch these 3 videos in order to be prepared for what we're going to cover in the course material. Now, matrix algebra, up until now, we've done all of these calculations in bivariate and multiple regression, and we've done them by hand. However, as models increase in complexity, and really what we might mean by that is by adding additional independent variables or predictor variables, the mathematics calculations underlying the solution also become extremely complex. So what we have to understand from this class is that most multivariate statistics are based in matrix algebra. They're not based in these geometric or algebraic equations that we've been doing for the first month or so, or first few weeks of this class. So understanding matrix algebra will help you better understand the material that we're going to cover in the end of 720 and throughout the end of the rest of the semester. Matrix algebra in general has 2 essential clarifications, or objectives: providing a compact method of expressing data and simplifying and clarifying the mathematics and the statistics. Now, a matrix is an n by k number of rectangles that stand for numbers, where n is the number of rows. So as we see here below, we have 3 rows, and k is the number of columns. We have 3 columns. Note that whenever we talk about matrices, we're always going to do rows by columns. So if I say something is a 3 by 3 matrix that we have here, it's going to be 3 rows, 3 columns. If I said something was a 2 by 4 matrix, it would have 2 rows and 4 columns. A matrix is named by a bold capital and labeled by its rows and columns. For example, what we have down here is matrix A, because of the bold A, and it's a 3 by 3 matrix. Any single element of a matrix is in reference to the row and column of that matrix that it applies. For example, if we wanted to find A1, 2, what we'd first do is look at row 1, and then we would look at column 2. That brings us to 4. A1 element, or the A1, 2 element equals 4. Now, the transpose of a matrix is is obtained by exchanging the rows and columns. This is denoted by A prime. So we have A over here, and we have A prime to the right. Given our A matrix, you're going to see how we take the transpose. So here we had we're going to take 2, 4, 3 is the first row. It actually becomes the first column in the transpose. Where 9, 2, 8 was the second row, it is the second column in the transpose, and 4, 1, 6 was the third row, it is now the third column in the transpose. So I want you to take an opportunity to take a few seconds to check your understanding. In the matrix I have to the right, this B matrix, I want you to identify the following elements: B23 and B32. Additionally, I want you to determine what the transpose is. I'm going to write the answer here, but pause this before I do so that you can test your own knowledge. Alright, so if I wanted to do B23, I would start off by going to row 2, and then I would go to column 3. So row 2, column 3 is going to be 5. B23 equals 5. Where B32 means I'd have to go to row 3, column 2, B32 equals -2. And if I wanted to do the transpose of the B matrix, which would be B prime, I'm going to change this so now the first row becomes the first column. So it would be 2, 4, 4, -6, and then it would be 6, 7, 5, -2, and then 8, -2, 4, 4. I put my brackets around it, and now B prime is also going to be labeled as it has 4 rows and it has 3 columns, so it is a 4 by 3 matrix. So make sure that you did that right. Alright, couple of things that we're going to finish off this first video with is some types of matrices that you should be aware of, many of which you're already familiar with. A symmetric matrix is a matrix where the same elements above and below the principal diagonal. By definition, the principal diagonal is this row down or diagonal down the middle. This is what we see in a correlation. A correlation is a symmetric matrix where the principal diagonal is 1.0 and then everything above it is identical to the material below it. There are some other symmetric matrices that we deal with, but the R matrix is one example. A column vector is a matrix with only one column. Therefore, it is a vector that has an n, which is the number of rows, by one column array of numbers. A vector is indicated with a lowercase letter that is bolded. A vector that we've used in this class is called a b-vector, which is what you saw when you would look at regression, or look at our regression coefficients, where in the b-vector, the first element is our y-intercept, and then we had our two unstandardized slopes. So looking at the example we used in Lecture 3, our y-intercept was 41.124, and then our b1 was 3.589, and our b2 was 0.087. You can see that in the SPSS over here to the right, where this is a b-vector. And that's what we were looking at. So I just pulled those numbers over. Later this semester, we're going to use vectors in another statistical analysis that we're going to do, which is MANOVA, which is the multivariate analysis of variance. When we write our hypotheses, we're going to reference them in terms of vectors, where each of the dependent variables are indicated within the vector. So these are the three subscales of the CSAI2, the Competitive State Anxiety Inventory: self-confidence, somatic anxiety, and cognitive anxiety. So I have, for Division 1 athletes, I expect their means to be equal to Division 3 athletes, but I'm looking across three dependent variables. We'll talk more specifically about that when we get to MANOVAs, but I want you to see that this is going to keep coming up throughout the semester. Another type of matrix is a row vector. Unlike a column vector where it's one column but many rows, a row vector is one row but many columns, so a 1 by n array of numbers. Therefore, a row vector is a matrix with a single row. Again, it's indicated by a lowercase letter that's bolded, and it's also just the transpose of a column vector, which is a really important point. So you got because we're going to use this concept and this concept a lot when we do the homework for matrix algebra. Row vectors are also noted with the prime as they are that transpose. So before, when I showed you the column vector for our b vector, if I wanted to take the transpose of our b vector, all I would do is take the 41.124 and put it as the first element, 3.589, now that is the 1 by 2 element, and the 0.087 is the 1 by 3. A diagonal matrix is a matrix that contains elements on the principal diagonal and no other elements are found, so they're all set to 0. Now, what you're going to see down here, a common matrix for that is called a V matrix, or the variances for all variables are set on the principal diagonal. So here we would have elements that are equal to sigma squared, or variance, and we have all other numbers set off to 0. Later this semester, you're going to see an important diagonal matrix, applications of diagonal matrices. And then an identity matrix is a special form of a diagonal matrix. In the identity matrix, all elements of the principal diagonal are set to 1, and all other elements are set to 0. This is considered the null hypothesis for a correlation matrix, because remember, the null hypothesis for any correlation is the assumption that R is not significantly different from 0. So what we're testing a correlation matrix to is an identity matrix. Alright, that takes us through the ends of the types of matrices. In video 2, you're going to start to look at basic arithmetic using matrices.